All right, video number 2, we're going to keep going with the examples. So this one has infinities in both bounds. So we're going from negative infinity to positive infinity of 1 over 1 plus x squared dx, and we want to simply determine whether this is convergent or divergent. Same exact concept. The only difference is we need to pick some value, some actual constant value to split this at, because we can't go from negative infinity to infinity, but what we can do is we can go from negative infinity up to a finite value, and then from that finite value up to infinity. So if this happens, we can split this. The best thing to do is to pick a nice convenient value. Well, if you already know that the antiderivative of this thing right here is going to be the inverse tangent, you want to pick something that you can actually evaluate the inverse tangent at, if possible. So we're going to probably split this thing at 0. It just makes the most sense in this case. It doesn't have to be, but it makes the most sense. So we're going to take and split the integral from negative infinity to 0 of 1 over 1 plus x squared plus the integral from 0 to infinity of 1 over 1 plus x squared. Now, since we're letting these infinities, because these are different, be different, we're going to let them be different variables. So we're not going to use t in this case. I'm going to use an a and a b. I'll let a be the left one, and I'll let b be the right infinity. So we're going to take the limit as a approaches negative infinity of integral from a to 0 of 1 over 1 plus x squared dx plus the limit as b approaches positive infinity of the integral of 0 to b 1 over 1 plus x squared dx. Now we can go ahead and take antiderivatives, which fortunately is the same for both. So I'll have the limit as a approaches negative infinity. It gets a little tedious to write all this out, but this is what we have to do, of inverse tangent of x evaluated from a to 0 plus the limit as b approaches positive infinity of the inverse tangent of x from 0 to b. And now we'll go ahead and plug these values in. So we'll take the limit as a approaches negative infinity of inverse tangent of 0 minus inverse tangent of a plus the limit as b approaches infinity of inverse tangent of b minus inverse tangent of 0. Now we've got some evaluation to go on, so we can simplify. Inverse tangent of 0. Remember, the question is, if I'm going to take the inverse tangent, it's really asking tangent of what gives us 0. Well, the tangent of 0 as an angle gives us 0, so this happens to be 0. This is still inverse tangent of a. I'm taking the limit as a approaches negative infinity, and this is the limit as b approaches positive infinity of inverse tangent of b minus, again, inverse tangent of 0 is 0. So now we have to figure out, if I plug in infinity or negative infinity in for a and b, what am I going to get? Well, this is really going to take you back to the idea of what the tangent function looks like. So if I kind of just sketch tangent, tangent looks something like this. But the biggest thing is that tangent has asymptotes, vertical asymptotes. And these occur at negative pi halves and pi halves. And then, of course, tangent is cyclical and keeps on going. But when we're talking about the inverses, we're really only talking about this as our domain anyway, from negative pi halves to pi halves. So what you want to think of is this is going to be plugging negative infinity in here. So it's going to be tangent, inverse tangent, excuse me, of negative infinity, or what angle is going to approach negative infinity. Well, this tangent approaches negative infinity as tangent approaches what angle? Well, it's going to go to negative infinity here as we approach negative pi halves. So this is 0 minus negative pi halves. And then this one, tangent as b approaches infinity, inverse tangent as b approaches infinity. So this y values are going to approach infinity as the angle approaches pi halves. So this is pi halves minus 0. So what I get is negative pi halves, which is pi halves plus pi halves equals pi. And since this is a finite value, this integral was convergent. All right, moving on. Example 4. For what values of p is the integral 1 to infinity of 1 over x to the p power dx convergent? So we're going to start off the same way. This is actually going to play a major role in what we're doing later on in the course. So we'll take the limit as, we'll go back to t's now, as t approaches infinity of the integral from 1 to t of 1 over x to the p power dx. Now remember that p here is just it's a constant, it's just a number. So we can really think of this as being x to the negative p. So we'll take the limit as t approaches infinity, integral from 1 to t, x to the negative p power dx. And since p is just a constant number, it's just a value, we can actually use the power rule, which says, I'm going to take the limit as t approaches infinity. If I take the power rule antiderivative, I add 1 to the exponent. So that's negative p plus 1, and then divide by the new exponent, which is negative p plus 1. And then I'm going to evaluate that from 1 to t. So this negative p plus 1 is a constant value. I can actually pull that out to the front of the limit in the denominator, so it's going to be 1 over that. 1 over negative p plus 1 times the limit as t approaches infinity of x to the negative p plus 1 from 1 to t. Now we can go ahead and evaluate. So we get 1 over negative p plus 1. Plugging in t, remember t goes in for x, not for p. X is the variable here. Limit as t approaches infinity, there we go, of t to the negative p plus 1 power minus, plugging in 1 for x, I get 1 raised to some power. The good news is 1 raised to anything is 1. So I get the limit, the limit as t approaches infinity of t to the negative p plus 1 minus 1. The limit of 1 as t approaches infinity is going to be 1. So it's this piece right here we have to figure out. And I apologize. I lost by 1 over negative p plus 1 out in front there. Okay, so I still have 1 over negative p plus 1. The limit as t approaches infinity. Now I can rewrite this. So what I can do is I can split this exponent up to be t to the negative p times t to the 1. And t to the negative p is the same thing as 1 over t to the p. So I can actually rewrite this as 1 over t to the p times t, and then minus 1. Almost there. So what I get is 1 over negative p plus 1 limit as t approaches infinity of t over t to the p power minus 1. So again, this goes back to the concept of limits. If p is 1, then what I would get is t over t. And that simplifies before you even plug anything in. You would get t over t as 1, and then you get 1 minus 1 is 0. That's actually a limit. That's okay. You can do that. But the problem is I can't have p be 1 because if p is 1, this outside piece here is undefined. I get 0 in the denominator. Oops. So in this case, p cannot actually equal 1. So p cannot be 1 because it makes this undefined. If p is a value which is less than 1, so maybe p is 1/2, I would get t to the 1 over t to the 1/2. Well, anytime the numerator's power is greater than the denominator's power and you take the limit as t approaches infinity, this is going to go off to infinity. So I'd have infinity minus 1, which is just some other form of infinity, times some constant. So it's going to be infinite. This would be divergent if p is, is less than 1. So that would be divergent. If p, however, is greater than 1, well, now maybe we're talking about like p is 2. So now I'd have t over t squared. Anytime the denominator has a greater power than the numerator, this whole thing is going to go to 0 as t approaches infinity. So this whole thing right here would go to 0. 0 minus 1 is negative 1. And then negative 1 times whatever's out here is just going to give me some kind of another constant. So anytime that p is greater than 1, this would be a convergent series. A convergent integral. So 1 over x to the p power is convergent for any value p greater than 1. And if you really think about what we did earlier, when p was 1, 1 over x, that was a divergent series. And we just said p can't be 1. It's actually divergent in this case because it doesn't work. And then if p is greater than 1, like 1 over x squared, that was convergent. And we did that earlier in the lesson. All right, moving on. So there's actually the exact thing that we just said. So if you didn't quite get it from what we just did, there it is in writing. If p is greater than 1, it's convergent. If p is less than or equal to 1, it is divergent. The second type, there is a discontinuous integrands. Well, what the heck does that mean? So the first thing is, let's discuss a positive function that's continuous. On a defined interval from a to b. However, look at b. B does not include its endpoints. And it has a vertical, because b is where the vertical asymptote is. So let's take a look at what that actually means. This would actually give us an infinite region in the vertical direction. So if here's a, and the function might do something like this, because b over here as a vertical asymptote. So as you can see, this would create an infinite discontinuity still, because this area technically keeps on going up this way. It's infinite in the vertical direction. It's the same concept, however. We can still try to figure out whether this thing is going to have a finite value or whether it's just not going to approach that asymptote quick enough that it would be infinite. So, if we want to find the area of t, it's going to approach a definite finite number as t approaches b from the left-hand side. Now notice the way this function is designed, this can only approach b from the left-hand side because nothing exists over here. So you do have to include that little symbol as it approaches b from the negative or left side. But otherwise the process is the same. What you want to note here is that we can actually use this formula even when f is not a positive function. So in this case, it could be a negative function as well. All right, let's just see some examples. I think that's the easiest way to kind of show this one. So here's your definitions in the box. All right, this is your type 2. If you have either a discontinuity on the right side or on the left side, you're still going to let t approach the where the place is discontinuous. You just have to indicate the direction, either from the left or from the right, depending on which side the function is coming from. Just like before, if you get an improper integral that has a finite value, it's going to be convergent. If you get an improper integral that does not have a finite value or gets infinity, then you're going to have divergent. If you happen to have a c value, so you're maybe you have a vertical asymptote in the middle of your integral, then you would have to split it up and do a to c and then c to b. Okay, we might see one like that, I don't remember. But here's the idea. Take a look at this integral real quick. This is the integral from 2 to 5 of 1 over square root of x minus 2. This thing is undefined when x equals 2, because if you plug 2 in, you get 2 minus 2, which is 0. You cannot divide by 0. Other than that, it would be fine on this integral. So the 2 gives you an infinite discontinuity. It's undefined because you have a vertical asymptote there. But the process is still the same. We have to take a limit. And then we'll say as t approaches, in this case we're approaching 2. Now this goes from 2 to 5. 2 is your leftmost value, so the only place you can approach it from is from the right side, because you're coming from 5 to 2 basically. So you have to do the as t approaches 2 from the positive side. We'll replace the 2 with a t. And then we've got 1 over square root of x minus 2 dx. And remember, you can rewrite this as limit as t approaches 2 from the positive side, integral from t to 5. We can rewrite that as x minus 2 to the negative 1/2 power dx. And you can either do a quick little u substitution or realize that if you do a u substitution, du is going to equal dx. So there's no constant that you're going to have to deal with. So really it's just treating this whole thing as basically a quantity to the negative 1/2 power. So when I take the antiderivative, I'll raise the power by 1. And then divide by the new power, which is dividing by 1/2 or multiplying by 2. And then I still have to take the limit as t approaches 2 from the right. And we have to evaluate this thing from t to 5. Okay, so we'll plug in the values. Take the limit as t approaches 2 from the right. Plugging in a 5, I get 2 times, what is that, 3, so square root of 3, minus 2 times plugging in t, I get the square root of t minus 2. Okay, and that is probably as simplified as I can get it. I could pull a 2 as a constant out to the front, but it's not going to matter right now. The limit of 2 square roots of 3 as t approaches anything, because this is constant, is 2 square roots of 3. It's a constant. This one I can plug 2 directly into here and actually get a value. Now if I plug 2 in here, I get 2 minus 2, which is 0, times 2 is still 0. So ultimately, this piece goes to 0. This one goes to the 2 square roots of 3. This is a finite value. Therefore, that integral was convergent. We actually could find the finite value, even though this had a vertical asymptote at x equals 2, because we got 2 square roots of 3 as the limit of the integral. All right, moving on. Let's determine whether the integral from 0 to pi halves of secant x dx converges or diverges. All right. Same concept. Now you do have to know something about your trig to realize that at 0 secant is fine, because secant is the reciprocal of cosine, so excuse me, 1 over cosine, 1 over 0 is fine. It's pi halves that gives us a problem. Cosine of pi halves is 0, which means secant is undefined there. So this pi halves is the value where we're going to have a problem. So we'll take the limit as t approaches pi halves. The only way I can approach pi halves is from the left, because we're going from 0 up to pi halves. So from the left of 0 to t secant x dx. Okay, this is one of them that I've given you guys. Again, it's probably best not to try and go through this the hard way and prove it. You just want to kind of memorize this integral right here. We're still going to have the limit as t approaches pi halves from the left. The antiderivative of secant of x is the natural log absolute value secant x plus tangent x. And we're going to evaluate that from 0 to t. So if we plug in t and 0, don't forget our limit. Plugging in t, we get natural log absolute value of secant t plus tangent t minus natural log absolute value of secant of 0 plus tangent of 0. Okay, this one we can evaluate. Tangent of 0 is 0, secant of 0 is 1. So what we get here is the natural log of 1, which is 0. So this whole piece goes away. This piece over here, we actually have to do some evaluation. So this is going to be plugging in pi halves. So we get natural log of secant of pi halves, but we already said that that's undefined. Here's the important part. The tangent, as we approach pi halves from the left, remember that approached infinity. So I'm going to get some kind of probably an infinity here plus another infinity. Well, that's just going to be another infinite value. So ultimately what we get is the natural log of some kind of absolute value of infinity, which goes to infinity, which means this one is divergent. And this is really knowing your trig values. So hopefully that's something that you guys do understand, and knowing the graphs and how they all look. All right, example number 7. This one has a discontinuity in the middle. 0 and 3 are both fine, but 1 in the middle is causing a discontinuity. So in this case, you actually have to split this to be the limit as t approaches 1. Now we're going to split this thing. The first one is going to go from 0 to t. So this can only approach t here, or 1, excuse me, from the left side of 1 over x minus 1 dx. And then the second one, the limit, now I can use the same t because t is still approaching the same value, it's just approaching it from different sides. And this is going to go from t to 3 of 1 over x minus 1 dx. Okay, and then we'll go ahead and take antiderivatives. So we have the limit as t approaches 1 from the left. This is going to be a natural log, so it's the natural log absolute value x minus 1 from 0 to t. Then we'll have the limit as t approaches 1 from the positive side of natural log absolute value x minus 1 from t to 3. Plugging in the values, we get the limit as t approaches 1 from the negative side of natural log absolute value of t minus 1 minus natural log. If I plug 0 in here, I get the absolute value of negative 1, which is 1, plus limit as t approaches 1 from the positive side. Natural log absolute value of plugging in 3, I get 2, minus natural log absolute value t minus 1. So again, this is going to come down to knowing the graphs of these things. If I were to look at this, the natural log of absolute value of t minus 1, so we put a 1 in here, this is going to be 0. Well, natural log of 0 doesn't exist, but the graph itself, again, natural log, looks something like this. As we approach 0, this thing is going to go to negative infinity. So what I get here is some form of negative infinity minus that's 0. This one is going to be plus the natural log of 2. And this one, again, is going to go to an infinity, negative, negative infinity, positive infinity, whatever it is. Minus a negative infinity. This whole thing is some form of infinity, a constant, and another form of infinity. This thing is infinite. Therefore, it is divergent. All right, we're already at about 28 minutes, but it doesn't make sense for one more problem to stop and do a new video, so we'll just go ahead and finish this off. Assuming that I can get this thing to go. All right, last example. Integral from 0 to 1 of natural log of x dx. So, again, the 0 is going to be the problem because that's where this thing has an infinite asymptote. So, limit as t approaches 0, we can only approach it from the right, of t to 1 ln x dx. Now, the natural log of x is not something we know an antiderivative of right off the top of our head, so we're going to have to think of other possibilities, and the first thing I can see is, okay, I've got a log here, I'm thinking integration by parts. So if we let u equal the natural log of x, that would make dv everything that's left over, which is dx. du is then going to be 1 over x dx, and v is x. So it's going to be uv minus the integral v du. So limit as t approaches 0 from the right of uv, so it's x ln x, minus the integral v du. X times 1 over x is just 1, so this is just 1 dx. So I can take the limit as t approaches 0 from the right of x ln x. The antiderivative here is just x, and we'll evaluate that from t to 1. So plugging this stuff in, plugging in 1, I get 1 ln of 1 minus 1 minus, plugging in t, we get t ln of t minus t. All right, let's see what we've got here. 1 natural log of 1. Natural log of 1 is 0, so that's gone. So that's going to be minus 1. This is going to be minus t ln t. That's going to be plus t. I still have to take the limit as t approaches 0 from the right. Well, the limit of negative 1 is negative 1. If I plug 0 into this t right here, I get 0. If I plug zeros in here, this is where we have a problem. This would give me 0 for this t, but the natural log, as we approach 0, goes to infinity. So I would get that form 0 times a negative infinity, which again is indeterminate. So we need to rewrite this somehow so that we can use L'Hopital's rule and try and figure this out. Well, t ln of t could be rewritten as, let's write it over here, t ln of t could be rewritten as the natural log of t over 1 over t. Now I can use L'Hopital's rule, taking the derivative of the top and the bottom is going to give me 1 over t, because that's the derivative of natural log of t. The derivative of this is like t to the negative 1, is going to be, what is it, negative 1 over t squared, I believe. You can double check that. This simplifies. Remember, don't try and plug these limits back in until you simplify this. This simplifies because that's 1 over t times negative t squared over 1, which is going to simplify to negative t. Now if I take the limit as t approaches 0 of this whole thing just goes to 0. So really what I get out of this whole thing is negative 1, which means that was convergent. All right, that is plenty long enough for this video. Hopefully that's all we'll need.